Hello everyone, good morning. Our project name is Operating System Pegging Simulator. My name is YUEHUI, and today I will introduce the background of our project, the problem we want to solve, and the main features of our simulator. Before I present, let me introduce my teammate. His name is YINGKAI. Okay, first let me explain why we choose this topic. Pegging is one of the most important concepts in operating system, but it is also one of the most difficult topics for students to understand. When learning peggs, we usually rely on like PowerPoint and slides or textbooks. They explain the theory, but it's difficult to imagine what is actually happening inside the concepts, a computer. For example, students need to understand the relationship between program pages, page table, and physical memory. But these concepts are very abstract. Many students end up memorizing the process instead of really understanding it. So our goal was to build a web-based virtual simulator that allows users to see the pegging process step by step. Users can also change the number of pages and memory frames, so they can explore different simulations instead of only look at one example. To solve this problem, we designed an interactive website. Our simulator focuses on making the pegging process easy to understand through virtualization. There are four main features. First, users can enter any number of program pages and physical memory frames, so the simulation is flexible. Yeah. And second one is users can run the simulation step by step using the next step button. This helps them clearly understand what happens during each stage. And the third one is if users want to see the whole process continuously, they can simply click Auto Run. We have an Auto Run button here. And the simulator will complete the animation automatically. And the last one is during the simulation, the page table, logical address, and physical memory are updated in real time. This allows users to easy to observe how virtual memory is translated into the physical memory. We develop it, we use HTML to build the website structure, and CSS for the style and interface and animations, and JavaScript to implement the pegging logic and user interactions. Okay, for the system design and architecture, let me pass it to my friends.
For the system design, we implemented a clear three-layer modular architecture: the control layer, the logic and translation layer, and the visualization layer. The interface connects the virtual address space, page table translation, and physical memory allocation on a single page. The flowchart breaks down key nodes, from initialization to simulation completion, to help users easily understand the system operation mechanism. This shows our core implementation. Based on user input, JavaScript dynamically creates elements for pages and frames. The most important address mapping algorithm relies on a simple mathematical formula: frame index equals step modular frame count. Upon clicking next step, the algorithm identifies the logical page, calculates its physical frame index, updates the UI, and fills the translation record into the page table. Here are two snapshots from our simulator. On the left, the initial load shows program page 0 being loaded into physical frame 0 as the progress bar starts. On the right, the continuous mapping shows that as the step counter increases, logical pages fill physical memory sequentially. The page table and progress bar update in real time, transforming abstract theoretical concepts into visual interactive dynamics. In conclusion, we successfully developed a fully functional paging simulator. It enhanced the learning experience and served as a great browser-based self-learning tool. In the future, we plan to expand features by adding page replacement algorithms like FIFO and LRU, and optimizing animation effects. That's all. Thank you for listening.